The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this is lecture 14. It's also the lecture before the exam on Tuesday evening. I thought I would just go ahead and tell you what the questions there are, so you could see. I haven't filled in all the numbers, but this will tell you, it's a way of reviewing, of course, to sort of see the things that we've done, which is quite a bit, really. And also, of course, topics that would not be in the exam. You can see that they're not in the exam. For example, topics from 1.7 on condition number or 2.3 on Graham-Schmidt that I can speak about a little bit. So those are the only thing I didn't fill in is the end time there. So I don't usually ask 4 questions. 3 is more typical. So it's a little bit longer, but it's not a difficult exam. And I never want, time to be the essential ingredient. So 7:30 to 9 is the nominal time, but it would not be a surprise if you're still going on after 9 o'clock a little bit. And I'll try not to, tear the paper away from you. So just figure that if you move along at a reasonable speed, and so you can bring papers, the book, whatever, anything with you. And I'm open for questions now about the exam. You know where 54-100 is? It's a classroom, unfortunately, not a... sometimes we'll have the top of Walker where you have a whole table to work on. That's this 54-100 in the tallest building of MIT out in the middle of the middle space out there is a large classroom. So if you kind of spread out your papers, we'll be okay. It's a pretty big room. Yeah. Questions? And of course, don't forget this afternoon in 190 rather than here. So review is in 190, 4 to 5 today. But if you're not free at that time, don't feel that you've missed anything essential. I thought this would be the right way to tell you what the exam is and guide your preparation for it. Questions? Yes, thanks.
How does the beam-bending equation number 1 relate to the oscillation equation number 2?
So these are 4 different questions. So this would be a question about, essentially about getting to this matrix and what it's about, A transpose CA.
In terms of when you're giving a beam-bending equation or a beam-bending question, it's the negative u double prime equals that. That's the equation you use, right?
Okay, I don't use beam bending for that. I'm thinking of elastic bar. Yeah, stretching equation, yeah. So the stretching equation, so the first one we ever saw, the stretching equation was just u double prime, or minus u double prime equal 1. And now that allows a C to sneak in, and that allows a matrix C to sneak in there. But I think you'll see how what they should look like. But that, yeah. Yeah. Oh, yeah. So this is section 2.2, directly out of the book. M will be the mass matrix. K will be the stiffness matrix. Yeah.
The notation K in chapter 1 is totally different because it's supposed to be a second difference.
Okay. So good point to say. In the very first section, 1.1, we gave the name K to a very special matrix, a specific one. But then later now, I'm using the same letter K for matrices of that type. That was the most special, simplest, completely understood case. But now I'll use K for stiffness matrices, and when we're doing finite elements in a few weeks, again, it'll be K. Yeah, same name, right. So here you'll want to create K and M and know how to deal with that. This was our only time-dependent thing. So I guess what you're seeing here is not only what time-dependent equation will be there, but also that I'm not going in detail into those trapezoidal difference methods. Important as they are, we can't do everything on the quiz, so I'm really focusing on things that are central to our course. Yeah. Good. Other questions? And very open for more questions this afternoon. Yeah. Others? Okay. So let me, I don't want to go on and do new material because we're focused on these things. And this course, the name of this course is Computational Science and Engineering. And by the way, I just had an email last week from the Dean of Engineering, or a bunch of us did, to say that the School of Engineering is establishing Center for Computational Engineering, CCE. Several faculty members there, and like myself in the School of Science and in the Sloan School, are involved with computation, and this new center is going to organize that. So it's a good development, and it's headed by people in Course 2 and Course 16. So if we're talking about computation, then I do have to say something about how you would actually do the computations and what are the issues about accuracy. Speed and accuracy is what you're aiming for in the computations. Of course, the first step is to know what problem is it you want to compute. What do you want to solve? What's the equation? That's what we've been doing all along. Now I just take a little time out to say, suppose I have the equation. When I write K, I'm thinking of a positive, symmetric positive definite or at least semi-definite matrix. When I write A, I'm thinking of any general, usually tall, thin matrix, rectangular, so that I would need least squares for this guy, where straightforward elimination would work for that one. And so my first question is, let's take these. So these are two topics for today. This one would come out of 1.7, that discussion with condition number. This one would come out of 2.3, the least squares section. Okay, so if I give you, and I'm thinking, the computational questions emerge when the systems are large. So I'm thinking thousands of unknowns here, thousands of equations at the least. Okay, so, the question is, let me just, I do Gaussian elimination here, ordinary elimination, backslash, and how accurate is the answer? And how do you understand? I mean, the accuracy of the answer is going to kind of depend on two things, and it's good to separate them. One is the method you use, like elimination, whatever adjustments you might make, pivoting, exchanging rows to get larger pivots. All that is in the algorithm, in the code. And then the second very important aspect is the matrix K itself. Is this a tough problem to solve, whatever method you're using, or is it a simple problem? Is the problem ill-conditioned, meaning K would be like nearly singular? Then we would know we had a tougher problem to solve, whatever method. Or is K quite well conditioned? I mean, the best condition would be when all the columns are unit vectors and all orthogonal to each other. Yeah, I mean, that would be the best conditioning of all. That condition number would be 1 if this K, which not too likely, is a matrix that I would call Q. Q, which is going to show up over here in this second problem. This Q stands for a matrix which has orthonormal columns. So you remember what orthonormal means. Ortho is telling us perpendicular. That's the key point. Normal is telling us that they're unit vectors, lengths 1. So that's the Q, and then you might ask, what's the R? And the R is upper triangular. Okay. Okay. So what I said about this problem, that there's the method you use, and also the sensitivity, the difficulty of the problem in the first place, applies just the same here. There's the method you use. Do you use A transpose A to find U hat, this is. Now we're looking for U hat, of course, the best solution. Do I use A transpose A? Well, you would say, of course, what else? That's that equation, that least squares equation has A transpose A, U hat equal A transpose B. What's the choice? But if you're interested in high accuracy and stability, numerical stability, maybe you don't go to A transpose A. Going to A transpose A kind of squares the condition number. You get to an A transpose A, that'll be our K, but its condition number will somehow be squared, and if the problem is nice, you're okay with that. But if the problem is delicate, now what does delicate mean for AU equal B? I'm kind of giving you a overview of the two problems before I start on this one and then that one. So with this one, the problem was, is the matrix nearly singular? What does that mean? Does MATLAB tell you? What does MATLAB tell you about the matrix? And that is measured by the condition number. What's the issue here is, when would this be a difficult, numerically difficult, sensitive problem? Well, the columns of A are not orthonormal. I mean, if they are, then you're golden. If the columns of A are orthonormal, then you're all set. So what's the opposite? Well, the extreme opposite would be when the columns of A are dependent. If the columns of A are linearly dependent and some column is a combination of other columns, you're in trouble right away. So that's like big trouble. That's like K being singular. Those are the cases. K singular here, dependent columns here, not full rank. So again, we're supposing we're not facing disaster, just near disaster. So we want to know, is K near to singular and how to measure that? And we want to know what to do when the columns of A are independent, but maybe not very. Maybe not very. And that would show up in a large condition number for A transpose A. You could, and this happens all the time. If you don't set up your problem well, then your experimental problem, you can easily get matrices A whose columns are not very independent, measured by A transpose A being close to singular. Right? Everybody here has got that idea. If the columns of A are independent, A transpose A is non-singular. In fact, positive definite. Then now we're talking about when we have that property, but we're kind of not very. The columns of A are not very independent, and the matrix A transpose A is not very invertible. Okay, so that's what the things are. And then just to say on this one, what's the good thing to do? The good thing to do is to call the QR code, which gets its name because it takes the matrix A and it factors it. Of course, we all know that LU is the code here that factors K. And QR is the code that factors A. into a very good guy, an optimal Q. It couldn't be beaten. And an R that's upper triangular, and therefore in the best, simplest form, you see exactly what you're dealing with. Let me continue this least squares idea, just so, because Q and R are probably not so familiar. Maybe the name Graham-Schmidt is familiar. How many have seen Graham-Schmidt? The Graham-Schmidt idea I'll describe quickly, but just do those words, those guys' names mean anything to you? Yes, if they do, quite a few, but not all. Okay, okay. And can I just say also, Graham-Schmidt is kind of our name for getting these two factors, and you'll see why it's very cool to have them, why this is a good first step. It costs a little to take that step, but if you're interested in safety, take it. It might cost twice as much as solving the A transpose A equation. So you double the cost by going this safer route. And double is not a big deal usually. Okay. So, I was going to say that Graham-Schmidt, that's the name everybody uses, but actually their method is no longer the winner. And I can, in section 2.3, and I'll try to describe a slightly better method than the Graham-Schmidt idea to arrive at Q and R. But let's suppose you got to Q and R. Then what would be the least squares equation? A transpose A U hat is A transpose B, right? That's the equation everybody knows. But now if we have A factored into Q times R, let me see how that simplifies. So now A is QR, and A transpose, of course, is R transpose Q transpose U hat, and this is R transpose Q transpose B. Same equation. I'm just supposing that I've got A into this nice form where Q has, where I've taken these columns that possibly lined up too close to each other, like, angles of 1 degree. And I've got better angles. I've got these columns of A are too close, so I spread them out to columns of Q that are at 90 degrees, orthogonal columns. Now, what's the deal with orthogonal columns? Let me just remember the main point about Q. It has orthogonal columns, right? And I'll call those Q's, Q1 to Qm. Okay. Then the good deal is what happens when I do Q transpose Q. So I do Q1 transpose, these are now rows, to Qn transpose, Q1 columns to Qn, and what do I get when I multiply those matrices? Q transpose times Q. I get I. Q1 transpose Q1, that's the length of Q1 squared is 1, and Q1 is orthogonal to all the others, and then Q2, you see I get it, the I. Q3, get an n by n, I get the identity matrix. Q transpose Q is I. That's the beautiful, just remember that fact, and use it right away. You see where it's used? Q transpose Q is I in the middle of that. So I can just delete that. I just have R transpose R, and now I can even simplify this further. What can I do now? So that's the identity. So I have R transpose R, but now I have an R transpose over here. So what am I left with? I'll multiply both sides by R transpose inverse, and that will lead me to R U hat equals, now so I'm knocking out R transpose inverse on both sides, Q transpose B. Well, that's, our least squares equation has become completely easy to solve. We've got a triangular matrix here. I mean, it's just back substitution. It's just back substitution now, and a Q transpose B over there. So a very simple solution for our equation after the initial work of A equal QR. Okay. But very, safe. Q is a great matrix to work with. In fact, people, codes are written so as to use orthogonal matrices Q as often as they can. All right, so that's, you had a look ahead of the computational side of 2.3. Let me come back to the most basic equations, just symmetric positive definite equations, KU equal F, and and consider, okay, how do we measure whether K is nearly singular? Okay, let me just ask that question. That's the central question. How to measure, when is K, which we're assuming to be symmetric positive definite, nearly singular? How to measure that? How to know whether we're in any danger or not? Okay. Well, first, I mean, you might think, okay, if it is singular, its determinant is 0. So why not take its determinant? Well, determinants, as we've said, are not a good idea numerically. For example, first, they're not fun to compute. Second, if they depend on the number of unknowns, right? If I just have twice the identity, imagine, suppose K is twice the identity matrix. You could not get a better problem than that, right? If K was twice the identity matrix, the whole thing's simple. Or if K is, suppose K is 1/1,000,000th of the identity matrix. Okay, again, that's a perfect problem, right? If K is 1/1,000,000th of the identity matrix, well, to solve the problem, you just multiply by 1,000,000, you've got the answer. So those are good, and we have to have some measure of bad or good that tells us those are good. Okay, so the determinant won't do, right? Because the determinant of 2i would be 2 to the nth, the size of the matrix. Or the determinant of 1/1,000,000th identity would be 1/1,000,000th to the n. Those are not numbers we want. What's a better number? Maybe you could suggest a better number to measure how close is the matrix to being singular. What would you say? I think if you think about it a little, so what numbers do we know? Well, eigenvalues jumps to mind, right? Eigenvalues jumps to mind. Because this matrix K, being symmetric positive definite, has eigenvalues, say, lambda 1 less than lambda 2, so on, up to less or equal lambda. So this is lambda max, and that's lambda min. And they're all positive, and so what's your idea of whether the thing's nearly singular now? Look at lambda 1, right? If lambda 1 is near 0, that somehow indicates near singular. So lambda 1 is sort of a natural test. Not that I intend to compute lambda 1. That would take longer than solving the system. But an estimate of lambda 1 would be enough. Okay. But my answer is not just lambda 1. And why is that? Because the examples I gave you, when I had twice the identity, what would lambda 1 be there in that case? If my matrix K was beautiful, twice the identity matrix, lambda 1 would be 2. All the eigenvalues are 2 for the identity matrix. Now, if my matrix was 1/1,000,000th of the identity, again, I have a beautiful problem. Just as good, just as beautiful problem. What's lambda 1 for that one? 1/1,000,000th. It looks not as good, right? It looks much more singular, but that's like just, it's not really there. So you could say, well, scale your matrix. And scaling the matrices, in fact, scaling individual rows and columns to get it, you know, you might have used, your unknowns might be somehow in the wrong units. So one of the answers is way big and the second component is way small. That's not good. But so scaling is important. But even then, you still end up with a matrix K, some eigenvalues, and I'll tell you the condition number. The condition number of K is the ratio of this guy to this one. In other words, 2K or 1,000,000 K or 1,000,000th K all have the same condition number, because those problems are identical problems. Multiplying by 2, multiplying by 1,000,000, dividing by 1,000,000 didn't change reality there. So, I mean, if we're in floating point, like, you know, it just didn't change. So the condition number is going to be lambda max over lambda min. And this is for symmetric positive definite matrices. So and MATLAB will print out that number. Or print an estimate for that number. As I said, we don't want to compute it exactly. Lambda max over lambda min. That measures how sensitive, how tough your problem is. Okay. And then I have to think, how does that come in? Why is that an appropriate number? I guess I've tried to give an instinct for why it's appropriate, but we can be pretty specific about it. In fact, let's do that now. Yeah, okay. So what would be the condition number of twice the identity? It would be 1. Perfectly conditioned problem. What would be the condition? Yeah, okay. Right. What would be the condition of a diagonal matrix? Suppose K was the diagonal matrix 2, 3, 4. The condition number of that matrix is 2, right? Lambda max is sitting there, lambda min is sitting there, the ratio is 2. Of course, any condition number under 100 or 1,000 is no problem. Roughly, the rule of thumb is that what's the rule of thumb? I think that maybe the number of digits in the condition number, the number of digits, what's it? Maybe if the condition number was 1,000, you would be taking a chance that your last 3 digits, in single precision, that would be 3 out of 3 bits. Yeah, somehow the log of the condition number, the number of digits in it, is some measure of the number of digits you lose. Because you're doing floating point. Of course, here that's a totally well-conditioned matrix. I wouldn't touch that one. I mean, that's just fine. But we can figure out of course, here's the point that I should make, because here's the computational science point. When this is our special K, our -1, 2, -1 matrix, -1, 2, -1 matrix of size n, the condition number goes like n squared. We could, because we know the eigenvalues of that matrix, we could see it. The largest eigenvalue, when n is big, say n is 1,000, and we're dealing with our standard second difference matrix, the most important example I could possibly present, then the largest the eigenvalues we actually are there in section 1.5. We didn't do them in detail. We'll probably come back to them when we need them. But the largest one is about 4. And the smallest one is pretty small. The smallest one is sort of like a sine squared of a small number. And so the smallest eigenvalue is of order 1 over n squared. And then when I do that ratio of 4, lambda max is just like 4. This lambda min is like 1 over n squared, quite small. That ratio gives me the n squared. So there's an indication. Basically, that's not bad. That's not bad. If n is 1,000 in most engineering problems, that gives you extremely good accuracy. Condition number of 1,000,000 you could live with. If n is 100, more typical, condition number of 10,000 is basically, I think, okay. I think okay, yeah, yeah. And yeah, I would go with it. But if the condition number is up, way up, then I'd think again, did I model the problem well? Okay, all right. So now I have to tell you, why is this inappropriate? How do you look at the error? So can I write down a way of approaching this, this KU equal F? So this is the first time I've used the word round-off error. So in all the calculations, in all the calculations that you have to do to get to U, those row operations, and you're doing them to the right side too, and you're taking, so all those are floating point operations in which small errors are sneaking in. And it was very unclear in the early years whether the millions and millions of operations that you do, additions, subtractions, multiplications, in elimination, could those like add up? If they don't cancel, you've got problems, right? But in general, you would expect somehow that these are just round-off errors. You're making them millions and millions of times. It would be pretty bad luck. I mean, like Red Sox 12th inning bad luck to have them pile up on you. So you don't expect that. Now, what you do solve, so what you actually compute, so this is the exact. This would be the computed. Let me suppose that the computed one is sort of there's an error. I'll call it delta U. That's our error. And it's equal to an F plus delta F. And this is the error, this is our round-off error. This is error we make. And this is error in the answer, in the final answer. Okay, now I would like to have an error equation, an equation for that error, delta U, because that's what I'm trying to get an idea of. No problem. If I subtract the exact equation from this equation, I have a simple error equation. So this is my error equation. Okay. And so that I want to compare this, estimate the size of that error compared to the exact. You might say, and you would be right, in saying, well, wait a minute, as you do all these operations, you're also creating errors in K. So I could have a K plus delta K here too. Actually, it wouldn't be difficult to deal with, and would certainly be there in a proper error analysis. And it wouldn't make a big difference. The condition number would still be the right measure. So let me concentrate here on the error in F. When subtracting one from the other gives me this simple error equation. Okay. So my question is, when is that error delta U big? When do I get a large error? And delta F I'm not controlling. I might control the size, but the details of it I can't know. So what delta f, and now I'll take worst possible here. Suppose this is of some small size, 10 to the minus something, times some vector of errors, but I don't know anything about that vector, and therefore I better take the worst possibility. What would be the worst? What right-hand side would give me the biggest delta u? Yeah, maybe that's the right question to ask. So now we're being a little pessimistic. We're saying what right-hand side, what set of errors in the measurements or from the calculations would give me the largest delta u? Well, so let's see, I'm thinking the worst case would be if delta f was an eigenvector with the smallest eigenvalue, right? If delta f is an eigenvector, is x1, the eigenvector that goes with lambda 1. Suppose the worst case, would be for that to be the first eigenvector. That would be the worst direction. Of course, it would be multiplied by some little number. Epsilon is every mathematician's idea of a little number. Okay, so epsilon x1. Then what is delta u? Then the worst delta u is what? What would be the solution to that equation? If the right-hand side was epsilon and an eigenvector, then this is the whole point of eigenvectors. You can tell me what the solution is. Is it a multiple of that eigenvector? You bet. If this is an eigenvector, then I can put in the same eigenvector there. I just have to scale it properly. So it'll be just this side. And what do I need? I think I just need lambda 1. The worst k inverse can be is like 1 over lambda 1. Right? If I claim that that's the answer, if the right-hand side is sort of in the worst direction, then the answer is that same right-hand side divided by lambda 1. Because if let me just check. If I multiply both sides by k, I have k delta u equal k. What's kx1? Everybody with me? What's kx1? Lambda 1 x1. So the lambda 1's canceled, and I got the epsilon x1 I wanted. Right. So no surprise. That's just telling us that the worst error is an error in the direction of the low eigenvector, and that error gets amplified by 1 over lambda 1. Okay, so that's brought lambda 1, lambda min, into it in the denominator. Now, here's another point. Second point now. So that would be the absolute error. But we saw with those factors of 2 and 1/millionth and so on that really it's the relative error. So I want to estimate not the absolute error, delta u, but the error delta u relative to u itself. So that if I scaled the whole problem, my relative error wouldn't change. So in other words, what I want to do is ask, in this case, what's the right-hand side? How big? Yeah, no, I want to know how small u could be, right? I'm shooting for the worst. The relative error is the size of u. Is the size of u compared? Sorry, maybe I should put it this way. The relative error is the size of the error relative to the size of u. And I want to know how big that could be. Okay, so now I know how big delta u could be. It could be that big. But u itself, how big could u be? How small could u be, right? U's in the denominator. So if I'm trying to make this big, I'll try to make that small. So when is u the smallest? Over there I said when is delta U the biggest. Now I'm going to say when is U the smallest. What F would give me point me in the direction in which U was the smallest? Got to be the other eigenvector, this end. The worst case would be when this is in the direction of xn, the top eigenvector. In that case, what is U? So I'm saying the worst F is the one that makes U smallest, and the worst delta F is the one that makes delta U biggest. I'm going for the worst case here. So if the right side is xn, what is U? Xn over lambda. Because when I multiply by k times xn brings me a lambda n, cancels that lambda n, I get it right. So there is the smallest U, and here is the largest delta U. And the epsilon is coming from the method we use, so that's not involved with the matrix K. So do you see I'm there? If I'm trying to estimate delta U over U, that's big. Delta U over the size of delta U over this, the size of delta U over the size of U is what? Delta U has some epsilon that measures the machine number of digits we're keeping, the machine length, word length, and so on. This is a unit vector over lambda 1. That delta U is over lambda 1. This U is in the denominator. Lambda n, U is down here, so the lambda n flips up. Do you see it? By taking the worst case, I've got the worst relative error. So that for other methods of other F's and delta F's, they won't be the very worst ones. But here I've written down what's the worst. And that's the reason that this is the condition number. So I'm speaking about sort of topics that are there in 1.7, trying to give you the main point. The main point is look at relative error, because that's the right thing to look at. Look at the worst cases, which are in the directions of the top and bottom eigenvectors. In that case, that relative error has this condition number, lambda n over lambda 1, and that's the good measure for, that measures how singular the matrix is. So 1/millionth of the identity is not a nearly singular matrix, because lambda max and lambda min are equal. That's a perfectly conditioned matrix. This matrix has condition number 2, 4 over 2. It's quite good. This matrix is getting worse with an n squared in there, if n is big, and other matrices could be worse than that, of course. Okay, so that's my discussion of condition number. I have to add one more thing. These eigenvalues were a good measure when my matrix was symmetric, positive, definite. If I have a matrix that I would never call K, a matrix like 1, 1, 0, and a million, okay, that I would never write K for that. Like, I would shoot myself first before writing K. So what are the eigenvalues lambda min and lambda max for that matrix? Are you up now on eigenvalues? We haven't done a lot of eigenvalues, but triangular matrices are really easy. The eigenvalues of that matrix are 1 and 1. The condition number should not be 1 over 1. That would be like bad. So instead, I would, if this was my matrix and I wanted to know its condition number, what would I do? How would I define the condition number of A? You know what I do whenever I have a matrix that is not symmetric. I get to a symmetric matrix by forming A transpose A. I get to a K. I take its condition number by my formula, which I like in the symmetric case, and then I would take the square root. So that would be a pretty big number. For that matrix A, the condition number of that matrix A is up around 10 to the 6th. The condition number of that matrix is up around 10 to the 6th, even though its eigenvalues are 1 and 1, because when I form A transpose A, those eigenvalues will jump all over. And then probably eigenvalues, this thing will have eigenvalues, way up, and the condition number will be high. Okay, so that's a little, you'll meet condition number. MATLAB shows it, and you naturally wonder, what is this? Well, if it's a positive definite matrix, it's just the ratio lambda max to lambda min, and it tells you as it gets bigger, that means the matrix is tougher to work with. Okay, we have just 5 minutes left to say a few words about QR. Okay, can I do that in just a few minutes? And much more is in the codes. Okay, what's the deal with QR? I'm starting with a matrix A. Okay, start with a matrix A. It's got, make it 2 by 2. A 2 by 2. Okay, it's got a couple of columns. Can I draw them? So it's got a column there, that's its first column, and it's got another column there. Maybe that's not a very well-conditioned matrix, right? Those are the columns of A, plotted in the plane, 2 space. Okay, so now the Graham-Schmidt idea is, out of those columns, get orthonormal columns. Get from A to Q. So the Graham-Schmidt idea is, out of these 2 vectors, 2 axes that are not at 90 degrees, produce vectors that are at 90 degrees. Actually, you can guess how you're going to do it. How am I going to, let me say, okay, I'll settle for that direction. That can be my first direction, Q1. What should be Q2? The other, if that direction is the right one for Q1, I say, okay, I'll settle for that. What's the Q2 guy? Well, what am I going to do? Graham thought of it and Schmidt thought of it. I think Schmidt was a little later, but it wasn't like that hard to think of it. What do you do here? You could, well, we know how to do projections from this least squares. So suppose what am I looking for? Yeah, subtract off the projection, right. Take the projection and subtract it off and be left with a component that's perpendicular. So this will be the Q1 direction, and this will be this guy E, that what we called E would tell me the Q2 direction. And then we could make those into unit vectors and we'd be golden. Right. And if we did that, we would discover that the original A1, A2, and A1, so this is the original first column, and the original second column would be the good Q1 and the good Q2 times some matrix R. So here's our A equal QR. It's your chance to see this second major factorization of linear algebra. LU being the first, QR being the second. So what's up? Well, compare first columns. First columns, I didn't change direction. So all I have here is some scaling R110. Some number times Q1 is A1. That direction was fine. The second direction, Q2 and A2, those involve also A1. So there's an R12 and an R22 there. Maybe the point was this came out triangular. And that's what makes things good. It came out triangular because of the order that Graham and Schmidt work. Graham and Schmidt settle the first one in the first direction. Then they settle the first two in the first two directions. If we were in 3 dimensions, there'd be an A3 somewhere here coming out of the board. And then the Q3 would come straight out of the board. Right? You can see, if you just see that, you get Graham-Schmidt completely. A1 is there. So is Q1. A2 is there. I've got to stay, I'm in the board still, in the plane of A1 and A2. This is the plane of Q1 and Q2. I'm just getting right angles there. A3, the third column in a 3 by 3 case, is coming out at some angle. I want Q3 to come out at a 90-degree angle. So that Q3 will involve some combination of all the A's. So if it was 3 by 3, this would grow to Q1, Q2, Q3, and this would then have 3 guys in its third column. But maybe you see that picture. So that's what Graham-Schmidt achieves. And I just can't let time run out without saying that this is a pretty good way. Actually, nobody thought there was a better one for a century. But then a guy named Householder came up with a different way to get and a numerically little better way. Numerically little better way. So this is the Graham-Schmidt way. Can I just put those words up here? So there's the Graham-Schmidt, the classical Graham-Schmidt idea, which was what I described was the easy one, easy to describe. And then there's a method called Householder, just named after him, that MATLAB would follow. That every good QR code now uses Householder matrices. It achieves the same result. But, and if I had a little more time, I could draw a picture of what it does. But there you go. So that's my lecture on, my quick lecture on numerical linear algebra, these 2 essential points. And I'll see you this afternoon. Let me bring those quiz questions down again for any discussion about the quiz.